Hi, my name is Gavin. This is the video for Design Assignment 2 for Computational Multiphysics. Here is my group. This time around, our problem had us using a trivection oven that used a skillet for uniform bottom heating, a microwave for interior heating, and a convection oven for exterior heating. We were given parameters and heat relations of the skillet, convection oven, and microwave, alongside the loaf that we were cooking that had crust and filling, both with different parameters, and we had 60 seconds to cook this pizza in the oven. The goal of this was to find the optimal power settings for the microwave and skillet such that the pizza achieved a maximum tastiness at the end of the 60 seconds, where tastiness comes from having all points in the loaf as close as possible to the ideal temperature of 75 degrees Celsius, as described by this relation. My role in this problem was I collaborated with the group to create a valid model of the problem, and for the report, I wrote the problem definition and the scripting portion. So our flex code was built from a template made based on previous examples in class using the heat equation, that can be seen right here where Q dot is defined here, and its different interpretations, such as volumetric heat generation from the microwave. Then the loaf cross-section was drawn two-dimensionally in flex. We can see the filling, the crust, and the skillet on the bottom. And here we can see the parameters that were given in the question defined. This is the power relation for the skillet, which we expect to be uniform along the bottom. That is what is seen in here. As you can see, all the same color, delivering it uniformly. Next, we have the convection heating model, which we expect to only heat the exterior of the crust, and that's exactly what we see in this simulation. And then next is the microwave heating, which we expect to only heat the interior, moving outwards towards the crust, which is then what we see in this simulation as well. To optimize processing time, we can make use of symmetry planes. In 2 dimensions, we can simulate half the cross-section here, and in 3 dimensions, we can actually only have to simulate a quarter of the cross-section, adding layers, of course, for the crust and caps. And then this is what the final 3D model should look like. However, this little lip for the skillet causes the n-grid limit to get surpassed. So in Flex PDE, we can't simulate that. This is what we only get in the student version. And without that lip, there's such a large degree of error that we're forced to use our 2D model to optimize this problem. And then after that was sorted out, all that was left was implementing the tastiness into Flex. So to test our model beyond just the oven power sources behaving as expected, we're going to ask a few additional questions. First, we're going to want to talk about the validity of the 2D approximation versus 3D. Then we're going to test if tastiness behaves as expected. And then we're going to test the case of no power in the skillet or the microwave behaving properly. So first off, with the 2D and 3D, this is a 3D simulation, 2D simulation with the same power values. We can see very similar scales, very similar results. Therefore, that validates that. And here is an end cap simulation where we can see, due to the different absorptivity, the crust is having a different temperature. Here is the final result with different configurations with consistent tastiness values between them. Next, if we move on to the tastiness consistency, since temperature and ideal temperature difference is raised to the fourth, small regions with large differences will greatly affect the tastiness. So we tested the behavior by increasing the air value to cause the crust to get a much larger non-ideal temperature, which should decrease the tastiness. And this is seen in testing right here with a lower temperature of only 120 degrees, and then 500 degrees. We can see the tastiness goes down. So that validates that. And next, we're going to test zero power in both the skillet and microwave. So we expect only heating to exist on the exterior, and that is exactly what we see here, with the interior and the bottom being much colder than the exterior from the convection heating. For our scaling case, we're going to cook the pizza for a very long time, which should increase the temperature a lot and cause our tastiness to be very small. And it's exactly what we see with 5.5 to the negative 12. So to optimize in Python, our program starts by defining our initial bounds, our divisions for the range initially, and the overall amount of grid searches we're going to do, which is 2. We're going to have an overall search and a zeroed-in search. So nested in the grid searches, we have our power value for loops. So first off, we have the skillet power in the first loop, and then nested as that is the microwave power. The structure for this is meant to take one skillet power in the range and then cycle through every single microwave power possible with that one skillet power, and then go back to the next skillet power and do the same with all the microwaves for that. And that's going to go over and over until every configuration for power for skillet and microwave has been simulated. Then afterwards, the maximum index of the tastiness values that are recorded is used to zero in a smaller range that is then used in the zeroed in grid search, and then the same process completes until we have our maximum values, and then that's all plotted down here in a 3D graph right here where we can see this dark blue dot being the maximum value. So then our optimal power settings for the skillet were 500 watts with an 84 kilogram error due to the step size, and the microwave was 2,300 watts with a 284 kilogram error from the step size. Both these together yield a maximum tastiness of about 0.02489. And the limits for this problem were the step size, since it would have taken a very long time to simulate smaller steps and more grid searches, so we decided 2 was sufficient for accurate results.